when I just started teaching differentiation, I think I told you that my favorite notation for the first derivative is dy by dx. And it's because it makes it so much easier to work with. And you will see exactly why I say that when we look at the topic that we're looking at now, chain rule. And chain rule assists us so much because, yeah, we know how to solve functions that are put together by summing them, finding their product, or dividing them. But chain rule makes life a bit easier in that, let's say that we have the function y equal 3x plus 4, right? We know how to find y prime. We just do it and done. That would be 3. Y prime equal 3. But what happens now if you have y is equal to 3x plus 4 cube? The methods of finding the derivative that we have looked on so far are telling us that, okay, in order for me to find y prime, I'm going to have to either say that this is going to be 3x plus 4 times 3x plus 4 times 3x plus 4 and then use product rule. Or I'm going to have to expand this out and then solve them using the sum and differences rule of differentiation. But chain rule is telling us no, you do not have to do all of that. So we definitely have to learn chain rule. Let's do that right now. So let me rewrite our function right here. Our function is 3x plus 4 all cubed. Now, we use the chain rule to solve composite functions. A composite function is where we have one function in another. So say, for example, that we have one function g of x is equal to 3x plus 4. And we have another function h of x, which is equal to x cubed. H of g of x is what we call a composite function because we have one function in another. And so h of g of x would be putting g of x anywhere you see x in h gives us 3x plus 4 all cubed, which is exactly what we have here. So how exactly does chain rule say that we should go about doing this? Let's see. Y is equal to 3x plus 4 all cubed, right? And we're going to say u is equal to 3x plus 4. So that means that y, written in terms of u, is u cubed. So if we differentiate y with respect to u, we get what? 3u squared. If we differentiate u with respect to x, what do we get? 3. Now you'll see exactly why I particularly like this denotation of the first derivative. Because dy by dx can be written as dy by du times du by dx. So it appears, and I will say falsely, it appears that the two du's cancel. Now I'm going to clear off those cancel signs because that is not the case. These are simply notations of the first derivative. They do not cancel, but I'm just saying this so that you can find an intuitive way of appreciating the concept of chain rule. So it's as though they cancel. So what happened? We're multiplying dy by du by dx in order to get dy by dx. So let's do that. So dy by du is 3u squared and du by dx is 3, leaving us with 9u squared. But what is u? U is 3x plus 4. And it's u squared. So dy by dx is 9 times 3x plus 4 all squared. Now, one very good application of chain rule is this when it comes to the solving of parametric equations. So normally, a coordinate is defined by 3, 2. That is an example of a coordinate where 3 would be the x value and 2 would be the y value. But there are times when we do not define coordinates like that. Rather, we use parameters to define coordinates. And so we would say that x is equal to t squared and y is equal to t cubed. That is one example of a parameterized equation, or rather a parametric equation. So all we would do is just plug in a value for t, and that value would determine x and y coordinates of a point. So we have a function, because this will actually form a function. We have a function given by the parametric equation x equal t squared and y equal t cubed. We are interested in finding the rate of change of y with respect to x. But t is here and t is not behaving very nicely, because these two t's are just not allowing me to find dy by dx. Now, what do we do? You know what? Let's just go with the flow, which is what I expect you to do in an exam. Instead of just sitting there and not knowing what to do, you actually start writing something and see where it takes you. So let's do that. Let's see where this takes us. So we have that x is equal to t squared. Let's find dx by dt. Dx by dt is equal to 2t. dy by dt is equal to 3t squared. So, where do we go from here? Where do we go from here? We want to find dy by dx, right? Now, let me give you a hint. We're going to use chain rule. So we have dy by dt. And we also have dx by dt. Now, if I were to multiply dy by dt by dx by dt, then that false cancelling that happens in my mind is not going to happen here, because the dt is not up here, because the dt is not at the top, it's in the denominator. So, how exactly am I going to get these two dt's to quote-unquote cancel? Well, I think it would be a good idea for me to divide these instead of actually multiplying them. So, if I were to divide these, I'm going to tell you the false story of what's happening in the background here. The false story is this. I am multiplying by the reciprocal of this, which would be dt over dx. And by multiplying dy by dt over dx, I am going to get dy by dx. Now scrap that story from your mind. I hope it helped you to understand the intuition, or to find a more intuitive way of understanding how to solve parametric equations using the chain rule. But as I said before, these are merely notations. I'm just helping you to get an intuitive understanding. So let's plug these things in. So we know, what should I clear off? Should I clear off this? We know that let's write this, dy by dx. We know that dy by dt is equal to 3t squared. And we're dividing by dx by dt, where dx by dt is 2t. So what does that leave us with? That leaves us with 3 over 2t. 3 over 2t. And that is how we find the first derivative of a parametric equation.